Okay, so we're looking at another function determining intervals of increasing and decreasing and any relative extrema that we have. So right here with cosecant of x, we know we're going to take our first derivative, and the derivative of cosecant is a negative cosecant of x cotangent of x. Now notice we were also given an interval in which we're looking at. We're not looking for every relative extreme or every interval of increasing and decrease, because if you remember, the graph of cosecant does something like this, and we would be here all day with all of those increases and decreases and relative minima and relative maximum. It just keeps going on and on and on. So we're only looking between negative pi and positive pi. So if you're thinking about our number line, instead of going from negative infinity to positive infinity, it's negative pi to positive pi. So now that we have our first derivative, we do have to find those critical values. And there's a few ways we can think about this. But first, I'm going to think about when our derivative equals 0. Right? So if I set this equal to 0, this is a negative cosecant of x cotangent of x. But I'm going to just first make this easier on myself. Divide both sides by -1, and we have 0 equals positive cosecant of x cotangent of x. If that negative possibly confuses you, just get it out of the way. And I can apply the zero product property now, thinking about when cosecant of x equals 0, when cotangent of x equals 0. Cosecant, of course, is 1 over sine. Cotangent of x is, of course, cosine over sine. Well, because the numerator is not 0, this right here will never equal 0. And we did just kind of mock up the cosecant of x function. It never crossed the x-axis. So this will never happen. Cosecant of x will never equal 0. So we don't get any critical values out of that one right there. But we can get some critical values, or hopefully at least one critical value out of this. When is cosine of x over sine of x equal to 0? Well, that would be when the numerator equals 0. When does cosine equal 0? That's the trick. We're really looking for when cosine equals 0, and we're looking for all the times that cosine equals 0 on this interval. And so if you're thinking unit circle, I know cosine equals 0 at pi over 2 and at 3 pi over 2. But thinking about on this interval, this would be at negative pi over 2 and positive pi over 2. So we got when our first derivative equals 0. It equals 0 at these two values. But we also need to know when our first derivative does not exist. That is also very important to us. So to find when the first derivative doesn't exist, again, we need to think about our first derivative. And I'll have to erase a lot of this stuff later when we get into our second part of our problem. We're thinking about when this first derivative, which if I rewrite these as a 1 over sine and a cosine of x over sine of x. Well, we also have problems when sine would be 0. If sine of x is 0, we would have division by 0 in both of those situations. So when is sine 0? Sine of x equals 0 at 0, at pi, at negative pi. Thinking about values again on this interval, I'm not going outside of that. Negative pi and positive pi are our in values, but 0 is well within this, and so we do need to put 0 on our number line. Okay, so we've got 0, we've got negative pi over 2, we've got positive pi over 2, and these are our critical values, and we need to think about what's going on in between these. Oh. And just to help us out, I'm going to go ahead and write this just in terms of sines and cosines because I have a feeling that is going to be helpful in a minute. Okay? So on our number line, think about the intervals. We've got negative pi to negative pi over 2. We've got negative pi over 2 to 0. We've got 0 to positive pi over 2. And we've got positive pi over 2 to pi. So we have 4 intervals. We have 4 sections of our graph. We need to think about what's going on. So in this first section from negative pi to negative pi over 2, what is our first derivative doing? We can think about some x value between negative pi and negative pi over 2. And I'm just going to cut it right down the middle. Negative 3 pi over 4, I think, is what I want to think about. I'm going to think about negative 3 pi over 4 because it is on this interval. And when I plug in negative 3 pi over 4, negative 3 pi over 4, of course, would be over here in this quadrant where both sine and cosine is a negative root 2 over 2. So if I plug it in over here, I would have a negative 1 over negative root 2 over 2 times negative root 2 over 2 divided by negative root 2 over 2. So this is a negative times a positive. So overall, this would be greater than 0. Notice this is a positive. A negative times a positive gives us a positive. So I can see right here that every x value on this interval is going to make my first derivative positive. And so on this interval, my original function, cosecant of x, y, is increasing on my interval from negative pi to negative pi over 2. Now negative pi over 2 to 0, I'm again going to think about one of those pi over 4 values. I'm going to think about negative pi over 4. And negative pi over 4 would be right here, where sine is positive. Sine is negative, cosine is positive. Sine is negative, cosine is positive. And they're just root 2 over 2s. So I'm just going to think about the signs. If I plug it in, I've got negative 1 over a negative times a positive divided by a negative. This is a negative times a negative times a negative. So my first derivative is negative on this interval. And because my first derivative is negative on this interval, I can say that y is decreasing on the interval from negative pi over 2 to 0. 0 to pi over 2. 0 to pi over 2, I'm going to think about positive pi over 4. It's in that first quadrant. Positive pi over 4 is when sine is positive Cosine is positive. They're both positive. Really, we don't even have to really think about pi over 4. It's just anything in this quadrant. They're both positive. And if they're both positive, we have a negative times a positive times a positive, which is telling me that my first derivative is negative on this interval. And if my first derivative is negative on this interval, I know that my original function is decreasing on the interval from 0 to pi over 2. Finally, we're looking at the quadrant from pi over 2 to pi. That's the stuff over here, where cosine is negative, sine is positive. And if cosine's negative, sine is positive, we'd have a negative times a positive times a negative. And so our first derivative would be positive, and so y would be increasing on our interval from pi over 2 to pi. Whew. Lots of stuff going on right there. All right, so we have a change from increasing to decreasing and a change from decreasing to increasing. Right here, it went from decreasing to decreasing. Because we had a change from increasing to decreasing, I know I have a relative increasing to decreasing would be a relative maximum at the x value of negative pi over 2. If we take a negative pi over 2 and we plug it back into the original function, negative pi over 2, remember cosine's 1 over sine. If we take a negative pi over 2, sine of negative pi over 2 is a negative 1, and so 1 divided by negative 1 is negative 1. So that point would be negative pi over 2, comma, negative 1. Right here, I switched from decreasing to increasing. It was going down, it comes back up, so there's a relative minimum at this x value of pi over 2. If we take pi over 2 and we plug it back into the original function, sine of pi over 2 is 1. 1 divided by 1 is a positive 1. So that point is pi over 2, comma, 1. Remember, don't get confused with what the first derivative and the original function tell you. The first derivative tells us about the slopes. It tells us about increasing and decreasing. The original function is where we get actual points. So that's where I was getting these actual points from here. Let's again take a look at all this, and hopefully all this is backed up by our graph for cosine of x. So I'm going to pull up my calculator. Y equals, clear out what I have. I want cosine, so I'm going to express it as 1 over sine of x. All right, we've got 1 over sine of x. Now, when you're graphing trig, it is important that your calculator's in radians. And I am going to just go ahead and make this window exactly what we want. We want to go from negative pi to positive pi in our x values. Negative pi to positive pi. I want to show exactly what we were just looking at. I want to, the scale is what you're counting by. Let's count by pi over 4s. It's a good interval for us. Our lowest y value, negative 10 to positive 10, that might be a little stretchy. Yeah, let's just see what that looks like. Okay, that does it fine. All right, so backing up what we saw over here, we have that increasing from negative pi to negative pi over 2. At negative pi over 2, we did have a relative maximum, and then it decreases to 0. It continues decreasing on the other side of 0. And at pi over 2, we had another relative minimum, and then it increased. Notice that at 0, our derivative was undefined, and that makes sense because our function's not continuous at 0. So all of this is backing up what we were seeing with the calculus, with the numbers.